In mathematics, a binary relation on a set A is a collection of ordered pairs of elements of A. In other words, it is a subset of the Cartesian product A2 equals A times A. More generally, a binary relation between two sets A and B is a subset of A times B. The terms correspondence, dyadic relation and two-place relation are synonyms for binary relation. An example is the divides relation between the set of prime numbers p and the set of integers z, in which every prime p is associated with every integer z that is a multiple of p. In this relation, for instance, the prime 2 is associated with numbers that include -4, 0, 6, 10. But not 1 or 9, and the prime 3 is associated with numbers that include 0, 6, and 9, but not 4 or 13. Binary relations are used in many branches of mathematics to model concepts like is greater than, is equal to, and divides in arithmetic, is congruent to in geometry, is adjacent to in graph theory, is orthogonal to in linear algebra, and many more. The concept of function is defined as a special kind of binary relation. Binary relations are also heavily used in computer science. A binary relation is the special case n equals 2 of an NARY relation RA1 times and that is, a set of n tuples where the jth component of each n tuple is taken from the jth domain Aj of the relation. An example for a ternary relation on Z times Z is lies between, and, containing e.g., the triples, and. In some systems of axiomatic set theory, relations are extended to classes, which are generalizations of sets. This extension is needed for, among other things, modeling the concepts of is an element of or is a subset of in set theory, without running into logical inconsistencies such as Russell's paradox. Formal definition. A binary relation R between arbitrary sets X and Y is specified by its graph G, which is a subset of the Cartesian product X times Y. The binary relation R itself is usually identified with its graph G, but some authors define it as an ordered triple, which is otherwise referred to as a correspondence. The statement G is read, X is R related to Y, and is denoted by XRY or R. The latter notation corresponds to viewing R as the characteristic function of the subset G of X times Y, i.e., R equals to 1, if G, and 0 otherwise. The order of the elements in each pair of G is important. If a B, then R and BRA can be true or false, independently of each other. Resuming the above example, the prime 3 divides the integer 9, but 9 doesn't divide 3. The domain of R is the set of all X such that X are Y for at least one Y. The range of R is the set of all Y such that X are Y for at least one X. The field of R is the union of its domain and its range. Is a relation more than its graph? According to the definition above, two relations with identical graphs but different domains or different codomains are considered different. For example, if, then, and are three distinct relations, where is the set of integers and is the set of real numbers. Especially in set theory, binary relations are often defined as sets of ordered pairs, identifying binary relations with their graphs. The domain of a binary relation is then defined as the set of all such that there exists at least one such that. The range of is defined as the set of all such that there exists at least one such that, and the field of is the union of its domain and its range. A special case of this difference in points of view applies to the notion of function. Many authors insist on distinguishing between a function's codomain and its range. Thus, a single rule, like mapping every real number x to x2, can lead to distinct functions and, depending on whether the images under that rule are understood to be reals or, more restrictively, non-negative reals. But others view functions as simply sets of ordered pairs with unique first components. This difference in perspectives does raise some non-trivial issues. As an example, the former camp considers surjectivity, or being on two, as a property of functions, while the latter sees it as a relationship that functions may bear to sets. Either approach is adequate for most uses, provided that one attends to the necessary changes in language, notation, and the definitions of concepts like restrictions, composition, inverse relation, and so on. The choice between the two definitions usually matters only in very formal contexts, like category theory. Example. Suppose there are 4 objects: ball, car, doll, gun, and 4 persons: John, Mary, Ian, Venus. Suppose that John owns the ball, Mary owns the doll, and Venus owns the car. Nobody owns the gun and Ian owns nothing. Then the binary relation is given as R equals. Thus the first element of R is the set of objects, the second is the set of persons, and the last element is a set of ordered pairs of the form. The pair, denoted by ball John, means that the ball is owned by John. Two different relations could have the same graph. For example, the relation is different from the previous one as everyone is an owner, but the graphs of the two relations are the same. Nevertheless, R is usually identified or even defined as G, and an ordered pair G is usually denoted as R. Special types of binary relations. Some important types of binary relations are between two sets X and Y listed below. To emphasize that X and Y can be different sets, some authors call such binary relations heterogeneous. Uniqueness properties. Injective. For all X and Z in X and Y in Y, it holds that if X are Y and Z are Y, then X equals Z. For example, the green relation in the diagram is injective, but the red relation is not, as it relates e.g. both X equals -5 and Z equals +5 to Y equals 25. Functional. For all X in X, and Y and Z in Y, it holds that if X are Y and X are Z, then Y equals Z. Such a binary relation is called a partial function. Both relations in the picture are functional. An example for a non-functional relation can be obtained by rotating the red graph clockwise by 90 degrees, i.e., by considering the relation X equals Y2, which relates e.g. X equals 25 to both Y equals -5 and Z equals +5. 1-to-1. Injective and functional. The green relation is 1-to-1, but the red is not. Totality properties. Left total. For all X in X there exists a Y in Y such that X are Y. For example, R is left total when it is a function or a multi-valued function. Note that this property, although sometimes also referred to as total, is different from the definition of total in the next section. Both relations in the picture are left total. The relation X equals Y2, obtained from the above rotation, is not left total, as it doesn't relate, e.g., X equals -14 to any real number Y. Surjective. For all Y in Y there exists an X in X such that X are Y. The green relation is surjective, but the red relation is not, as it doesn't relate any real number X to e.g. Y equals -14. Uniqueness and totality properties. A function. A relation that is functional and left total. Both the green and the red relation are functions. An injective function. A relation that is injective, functional, and left total. A surjective function or surjection. A relation that is functional, left total, and right total. A bijection. A surjective 1-to-1 or surjective injective function is said to be bijective, also known as 1-to-1 correspondence. The green relation is bijective, but the red is not. Difunctional. Less commonly encountered is the notion of difunctional relation, defined as a relation R such that R equals R minus 1 R. To understand this notion better, it helps to consider a relation as mapping every element XX to a set XR equals YY XRY. This set is sometimes called the successor neighborhood of X in R. One can define the predecessor neighborhood analogously. Synonymous terms for these notions are after set and respectively for set. A difunctional relation can then be equivalently characterized as a relation R such that wherever X1R and X2R have a non-empty intersection, then these two sets coincide. Formally x1r x2r implies x1r equals x2r. As examples, any function or any functional relation is difunctional. The converse doesn't hold. If one considers a relation R from set to itself, then if R is both transitive and symmetric, then it is also difunctional. The converse of this latter statement also doesn't hold. A characterization of difunctional relations, which also explains their name, is to consider two functions f, a c and g, bc, and then define the following set which generalizes the kernel of a single function as joint kernel. Ker equals A times B, F equals G. Every difunctional relation R A times B arises as the joint kernel of two functions f, a c and g, bc for some set C. In automata theory, the term rectangular relation has also been used to denote a difunctional relation. This terminology is justified by the fact that when represented as a Boolean matrix, the columns and rows of a difunctional relation can be arranged in such a way as to present rectangular blocks of true on the main diagonal. Other authors, however, use the term rectangular to denote in any heterogeneous relation whatsoever. Relations over a set. If x equals y, then we simply say that the binary relation is over x, or that it is an indoor relation over x. In computer science, such a relation is also called a homogeneous relation. Some types of indoor relations are widely studied in graph theory, where they are known as simple directed graphs permitting loops. The set of all binary relations REL on a set X is the set 2x times x, which is a Boolean algebra augmented with the involution of mapping of a relation to its inverse relation. For the theoretical explanation, see relation algebra. Some important properties of a binary relation R over a set X are reflexive. For all x in X, it holds that x are x. For example, greater than or equal to is a reflexive relation, but greater than is not. Irreflexive. For all x in X, it holds that not x are x. For example, greater than is an irreflexive relation, but is not. Correflexive. For all x and y in X, it holds that if x are y, then x equals y. An example of a correflexive relation is the relation on integers in which each odd number is related to itself and there are no other relations. The equality relation is the only example of a both reflexive and correflexive relation. The previous three alternatives are far from being exhaustive, e.g., the red relation y equals x2 from the above picture is neither irreflexive, nor correflexive, nor reflexive, since it contains the pair, and, but not, respectively. Symmetric. For all x and y in X, it holds that if x are y, then y are x. Is a blood relative of is a symmetric relation, because x is a blood relative of y if and only if y is a blood relative of x. Antisymmetric. For all x and y in X, if x are y and y are x, then x equals y. For example, is antisymmetric. Asymmetric. For all x and y in X, if x are y, then not y are x. A relation is asymmetric if and only if it is both antisymmetric and irreflexive. For example, greater than is asymmetric, but is not. Transitive. For all x, y and z in X, it holds that if x are y and y are z, then x are z. For example, is ancestor of is transitive, while is parent of is not. A transitive relation is irreflexive if and only if it is asymmetric. Total. For all x and y in X, it holds that x are y or y are x. This definition for total is different from left total in the previous section. For example, is a total relation trichotomous. For all x and y in X, exactly one of x are y, y are x, or x equals y holds. For example, greater than is a trichotomous relation, while the relation divides on natural numbers is not. Right Euclidean. For all x, y and z in X, it holds that if x are y and x are z, then y are z. Left Euclidean. For all x, y and z in X, it holds that if y are x and z are x, then y are z. Euclidean. An Euclidean relation is both left and right Euclidean. Equality is a Euclidean relation because if x equals y and x equals z, then y equals z. Serial. For all x in X, there exists y in X such that xry is greater than is a serial relation on the integers. But it is not a serial relation on the positive integers, because there is no y in the positive integers such that 1 greater than y, however, is less than, is a serial relation on the positive integers, the rational numbers and the real numbers. Every reflexive relation is serial. For a given x, choose y equals x. A serial relation can be equivalently characterized as every element having a non-empty successor neighborhood. Similarly, an inverse serial relation is a relation in which every element has non-empty predecessor neighborhood. Set like, for every x in X, the class of all y such that y(X) is a set. The usual ordering less than on the class of ordinal numbers is set like, while its inverse greater than is not. A relation that is reflexive, symmetric, and transitive is called an equivalence relation. A relation that is symmetric, transitive, and serial is also reflexive. A relation that is only symmetric and transitive is called a partial equivalence relation. A relation that is reflexive, antisymmetric, and transitive is called a partial order. A partial order that is total is called a total order, simple order, linear order, or a chain. A linear order where every non-empty subset has a least element is called a well order. Operations on binary relations. If R, S are binary relations over X and Y, then each of the following is a binary relation over X and Y. Union. Rs X times Y, defined as Rs equals R or S. For example, is the union of greater than and equals. Intersection. Rs X times Y, defined as Rs equals R and S. If R is a binary relation over X and Y, and S is a binary relation over Y and Z, then the following is a binary relation over X and Z. Composition. SR, also denoted R, S, defined as SR equals, there exists YY, such that R and S. The order of R and S in the notation SR, used here agrees with the standard notational order for composition of functions. For example, the composition is mother of, is parent of, yields, is maternal grandparent of, while the composition is parent of, is mother of, yields, is grandmother of. A relation R on sets X and Y is said to be contained in a relation S on X and Y if R is a subset of S, that is, if XRY always implies XSY. In this case, if R and S disagree, R is also said to be smaller than S. For example, greater than is contained in. If R is a binary relation over X and Y, then the following is a binary relation over Y and X. Inverse or converse. R-1, defined as R-1 equals R. A binary relation over a set is equal to its inverse if and only if it is symmetric. See also duality. For example, is less than, is the inverse of, is greater than. If R is a binary relation over X, then each of the following is a binary relation over X. Reflexive closure. R equals, defined as R equals XX, R or the smallest reflexive relation over X containing R. This can be proven to be equal to the intersection of all reflexive relations containing R. Reflexive reduction. R, defined as R equals R, XX, or the largest irreflexive relation over X contained in R. Transitive closure. R plus, defined as the smallest transitive relation over X containing R. This can be seen to be equal to the intersection of all transitive relations containing R. Transitive reduction. R minus, defined as a minimal relation having the same transitive closure as R. Reflexive transitive closure. R asterisk, defined as R asterisk equals, the smallest pre-order containing R. Reflexive transitive symmetric closure. R, defined as the smallest equivalence relation over X containing R. Complement. If R is a binary relation over X and Y, then the following two. The complement S is defined as XSY if not XRY. For example, on real numbers, is the complement of greater than. The complement of the inverse is the inverse of the complement. If X equals Y, the complement has the following properties. If a relation is symmetric, the complement is 2. The complement of a reflexive relation is irreflexive and vice versa. The complement of a strict weak order is a total preorder and vice versa. The complement of the inverse has these same properties. Restriction. The restriction of a binary relation on a set X to a subset S is the set of all pairs in the relation for which X and Y are in S. If a relation is reflexive, irreflexive, symmetric, antisymmetric, asymmetric, transitive, total, trichotomous, a partial order, total order, strict weak order, total preorder, or an equivalence relation, its restrictions are 2. However, the transitive closure of a restriction is a subset of the restriction of the transitive closure, i.e., in general not equal. For example, restricting the relation X is parent of Y to females yields the relation X is mother of the woman Y. Its transitive closure doesn't relate a woman with her paternal grandmother. On the other hand, the transitive closure of is parent of is ancestor of. Its restriction to females does relate a woman with her paternal grandmother. Also, the various concepts of completeness do not carry over to restrictions. For example, on the set of real numbers, a property of the relation is that every non-empty subset S of R with an upper bound in R has a least upper bound in R. However, for a set of rational numbers, this supremum is not necessarily rational, so the same property does not hold on the restriction of the relation to the set of rational numbers. The left restriction of a binary relation between X and Y to a subset S of its domain is the set of all pairs in the relation for which X is an element of S. Algebras, categories, and rewriting systems. Various operations on binary and/or relations can be treated as giving rise to an algebraic structure, known as relation algebra. It should not be confused with relational algebra, which deals in finitary relations. For heterogeneous binary relations, a category of relations arises. Despite their simplicity, binary relations are at the core of an abstract computation model known as an abstract rewriting system.